Can you see my computer screen here that I'm sharing with you?
Yes, Doctor.
Okay, thank you. Um, I have uploaded 3 samples of test 2. Sample test 2A, sample test 2B, sample test 2C, and I've also uploaded 3 samples of final exams. Yeah. So let's look at the questions given in the samples, and then I encourage you to try, some of them. Yeah. If possible, try all of them. Yeah. Okay. To practice. And I've also uploaded the vector valued functions note, which we discussed yesterday. And also a brief review on vectors. Yeah, this is taken from Yusuf Yaqub's book in the Appendix F. It's just a one-page review on vectors, something that you have studied last semester. Yeah.
Doctor, I have question.
Yes.
Test two cover until what chapter, Doctor?
If you look at the samples, suppose I click this sample test 2A. Okay, it's all about double integrals and triple integrals.
Double and triple integral.
Yeah, double and triple integrals, also some of the applications, Yeah, so that's what will be covered for your test. Okay, if you look at the other 2 samples, they are all of the same format, all questions concerning double integrals, triple integrals, and applications such as volume, mass, or maybe centroid or what center of gravity. Okay, so that's okay. The final exam will be a comprehensive. Let's take a look at this sample final exam A. This is comprehensive. I mean, all topics will be covered here. See, question number 1 is about functions of several variables. Question number 2 is about double and triple integrals. And question number 3 is about vector valued functions. Yeah, vector valued functions. And then question 4 is also about calculus vector, line integrals. Question number 5 is regarding surface integrals, and Stokes theorem and Gauss theorem here. Okay, so more emphasis is given on vector calculus. Yeah, on vector calculus. 3 questions on vector calculus, isn't it? Yeah, question 3, 4, 5 are related to vector calculus. Yeah, so more emphasis is given on vector calculus in the final exam. And regarding your test 1, here I have also I did some analysis, the mark distribution, For example, 3 students have obtained marks between 13.5 to 15. 1 student have obtained a mark from 12 to 13. 2 students have obtained mark 11.5. 3 students have obtained marks between 10.5 to 11, and so on. Okay, so this is the distribution of test 1 for this class here. So if I were to grade this test 1, then it is what is shown here. So for those who obtain 13.5 to 15, that can be considered as A plus. The student who obtained 12 to 13, that can be considered a grade A and so on. Yeah. Okay. So I considered students who have achieved 6 or higher. I have considered them that they pass the test 1. For those below 6, I considered you have not achieved the minimum standard. So people in this group need to work harder. But there's still chance for you to improve your grade. Because this is just 15%. We have 85 marks which we have not taken into account yet, from the assignment, from test 2, and from the final exam. So that doesn't mean that you get a C in test 1, you will get C in the end. So we have 85 remaining marks which have not been taken account yet. Okay, so there's still room for improvement. So I think so you need to change. Okay, you need to change. If previously you did not ask questions in class, or maybe now you need to start asking more questions. If in the previous you did not do a lot of practice, answering questions in the book or in the sample test, or then you need to do more work, to put in more effort. And maybe in the past, you even for group assignments, you copied each other from different groups, or someone else is just doing all the work and the rest are just like passengers. So I mean, you need to change, in order to achieve better marks for the upcoming assessments. Okay, so there's still room for improvement here. And it doesn't mean that a person who get A will also get A towards the end of the semester. It depends on very much on how marks you will. There's how many marks you will get. Okay, for the remaining assessments. Yeah. So this is. I mean, the reason I show this so that you can see where you stand among other students in the class, right? Okay, let's continue with our lecture. Let's see what we have discussed yesterday. I have introduced to you this concept of vector valued functions. Yeah, vector valued functions in general is a function that takes a real parameter t to a vector. Yeah, so this is the general form of a vector function in two-dimensional space, and the one below is a general form of a vector valued function in a three-dimensional space. Yeah, it's also called a position vector. Yeah? So in general, the vector changes with t. Okay, the vector changes it changes with t. So if we trace the tip of the vector, okay, we trace a curve here, red shown as a red curve here in space. Yeah, so that's why it's also called a position vector. So the functions, the coefficients of the vectors I, j, k, they are called the components. Okay, they are called the components of component functions of RT. All the component functions are real valued functions here. So we look at some examples of the determining the domain of a vector valued functions, and then we look at a problem on sketching. Yeah, sketching a vector valued function. Okay. So okay, you have any question regarding our lecture? Any question?
Not yet, Doctor.
Not yet. Okay, thank you. Okay, let's do an example. So as a note. Oh, no, let's make a new file. Okay, let me say something. Yeah, when I mark your test one, I see this one common mistake, you know. So example, when you want to solve a y squared equal to say 9/4, then how do you write the solution? It is y equal to, this actually, one should write it as plus or minus 9/4. Okay, and then the square root of 9/4 is the same as 3/2. Okay, so this is the correct way of writing the solution. But in the test one, I see sometimes students write it in this way: y equal to square root of 9/4 equal to plus or minus 3/2. That is not correct. Yeah, the square root of 9/4 is positive. It's always give us the positive value. So this is not correct way of writing. Yeah, you should write the plus or minus in front of the square root sign. Yeah. So please don't repeat this kind of calculation. Yeah. So this is basic, you know. This is basic mathematics. You should be able, as a university student, you should not make this kind of mistake. Yeah. Okay, so that's just a remark there. Okay, let's go back to this vector valued function. In general, the vector function, say f of t equal to x naught plus at times I plus y naught plus bt times j plus z naught plus c times t times a vector k always represent a line in space. Okay, represents a line in space. Okay, yeah, that passes through the point x naught, y naught, z naught, and parallel. Okay, and parallel to the vector ai plus bj plus ck. Okay, so this is a fact. The vector function, because you look at the coefficients of vectors I, j, k, they're all linear, right? They're all linear in T. So that's why this vector function represents a line in space. Okay, that passes through the point x naught, y naught, z naught, and parallel to the vector ai, bj, ck. So as an example, suppose you want to sketch the vector function, say let's call it g of t. doesn't have to be always F or R. So let's call it G here. 2 plus 3 Ti plus minus 1 plus Tj minus 2Tk. Okay, I want to sketch this vector function. So it is a line, okay, according to the above explanation. This vector function is a line in space, yeah. So if you make the comparison, the first component is x naught plus at. The second component function is y naught plus bt. And the third component function is z naught plus ct. Okay, so it is so g of t is a line, in space that passes through the coordinate x naught, y naught, z naught. So in this example, x naught is equal to 2, y naught equal to minus 1, and z naught is 0, right? 0 there, yeah. And parallel to the vector ai plus bj plus ck. So if you make the comparison, a is equal to 3, b is equal to 1, and c is equal to minus 2, okay, minus 2k. So now we have enough information to sketch the vector function g. So this is x, y, and z. So where is the point 2, minus 1, 0? 2, minus 1, 0. Where is it? Yeah. So let's make a scale here. This is 2, 1, 1, minus 1. So it is behind. It is in the negative. I'm sorry. The top the vertical axis should be z. Should be y. It should be y. Yeah. So minus 1, let's say it's over here. So 2 minus 1, 0. 2. You measure 2 units along the positive axis, and then 1 unit along the negative y-axis. So, and then z is 0, right? So that is the point 2 minus 1, 0. Yeah, so this is the point 2 minus 1, 0. Yeah. And a line that passes through this point and parallel to the vector 3i plus j minus 2k. So now let's sketch this vector. 3i means we go 3 unit along the 3 units along the positive x-axis, and then plus j. So this is 1. Okay. And then minus 2 unit downwards, right? Then because z is minus 2. So we measure minus 2 units. So this is minus 1, minus 2, say. Yeah. So this is the point. The point 3, 1, minus 2. So we draw a vector from the origin to this point. So now we want to draw a line that is that passes through 2, minus 1, 0, and parallel to this vector in green here. So it's in the pointing in a downward direction, right? So it's something like this, yeah. Okay. So, for example, what is g when t is minus 1? If I replace t equal to minus 1 in the vector valued function g, it is equal to, when t is minus 1, 2 minus 3 is minus I, minus 2j plus 2k, right? 2k, yeah. Minus 1, minus 2 plus 2k there. Yeah, so maybe somewhere. And then when t is 0, when t is 0, it is 2i plus minus j minus 0k. Minus 0k. When t is, this is in the increasing t, right? In this increasing t, yeah. When t equal to 1, this 5i and t equal to 1 plus 0j and t equal to 1 minus 2 minus 2k, yeah. Yeah. Minus 1 and t equal to, yeah. When t equal to minus 1, it's minus 1 minus 2. It's minus 1. And then minus 2. Yeah, plus 2. Okay, something like that, yeah. It's minus t equal to minus 1. X equal to minus 1. Yeah. Okay. So it is easy to sketch a line in space if we know which point it passes through and to which vector it is parallel. Yeah. You have any question? Yeah.
Nak tanya, yang arah tu kita assume dulu ke ataupun kita masukkan nilai negative 1, 0 dengan 1 dulu baru dapat?
We can do actually this is enough. Yeah, this is enough. Yeah. I mean, no need to plot the points. What minus 1? No need. Yeah, this is just I'm doing extra work here. But actually, what I've shown you is enough, right? Yeah. I mean, if you know a point and you know the vector, right, to which it's parallel, that's enough. Yeah. This is just extra. I'm just the one, the calculation t equal to minus 1, t equal to 0, t equal to 1 is actually just extra work here.
Ya, tak.
Okay. This 1 minus 2 and then 2, isn't it? Yeah. Two minus 1 is 0, 5, 0, minus 2. Okay. There's also such a question on vector curve, vector function sketching. In the final exam, I've seen it. Let me see, where is it? So this is what I call as sample A. Here it is. Okay, let's see this. Let's try this. Okay, let's do another example here. This is sample final exam. Yeah. You're given this vector. It's a position vector. Sketch the vector function R for t between 0 up to 2 pi. Okay. How do we solve this? Now, we can think of this RT as this is, or this can, in general, can be, RT can be regarded as XTI plus YTJ plus ZTK, right? Having components XT, YT, ZT. So that means here XT is equal to 1/4 cosine T, YT equal to sine T, and ZT is a constant here, which is -4. Okay, from the given vector function, you can determine the components XT, YT, ZT. Look at the XT, YT. It further implies what? For example, from xt we have cosine t equal to 4x, right? And then sine t is equal to y, isn't it? Yeah. So we can eliminate t. Okay, we can eliminate t from the identity cosine squared t plus sine squared t equal to 1. So we get 4x squared plus y squared equal to 1. So this is 16x squared plus y squared equal to 1. Okay. Now what is this equation? What is the graph of this equation?
Circle.
No. A circle has the coefficient, same coefficient for x squared and y squared.
Ellipse.
Ellipse, yeah. You need to recall all these basic things, an ellipse has the general form x squared over a squared plus y squared over b squared equal to 1. Okay? Yeah. So we can rewrite this as x squared over 1 over 4 squared plus y squared over 1 squared equal to 1, right? So therefore a is equal to 1/4 and b equal to 1. That it on the xy plane it is an ellipse. Okay, on the xy plane it is an ellipse, but here this ellipse is on the plane z equal to -4. Remember we have this extra equation here, so that means this ellipse is on the plane z equal to -4. So now we want to sketch this ellipse on the plane z equal to -4. This is x, this is y, z. So -4 is down here. Let's label this as -4. So we want to sketch this ellipse. on the plane the plane z equal to -4 is a horizontal plane, right? This is a horizontal plane. On the xy plane, it is 1/4. X is equal to 1/4. Y equal to 1. On the xy plane, it is an ellipse that looks something like this. Okay. So this is -1/4. This is -1. But the blue ellipse is on the xy plane, so we need to bring it downward 4 units. Okay, you need to sketch this ellipse on the xy plane, on the plane z equal to 4. So we have something like this, I guess. All right. Yeah. So this ellipse is sitting on the plane z equal to -4. Okay. Now we need also to indicate the direction of the ellipse. Is it clockwise or counterclockwise from above? Yeah. When t is 0, okay, where is that point? When t is 0, and t equal to 0, we have x equal to 0, right? Y equal, no, 1/4. Y equal to 0, z equal to -4. So it's here. It is over here. Yeah, when t is 0, it's there. Yeah, when t equal to pi over 2, x is equal to, when t cosine pi over 2 is 0, y equal to sine pi over 2 is 1, and z is the same. So it's somewhere here. This is the point when t equal to pi over 2. So it is in this direction. If you look from above, it is in a counterclockwise direction. All right. Any question? Okay, so sometimes we do have questions on vector curve, vector function sketching, in the final exam. Yeah. But for more complicated vector valued function, okay, of course sometimes we have to use computer to help us sketch the what? Yesterday I showed you the helix, right? The helix yesterday. Yes, yesterday I showed you some sketches of vector function, with the help of this software, Mathematica here. This one is a helix. Xt is cosine t, yt is sine t, zt equal to t. So it is a spiraling. It is a curve that spiral upwards. Yeah. And I showed you yesterday. This ellipse, this spiral sits on the surface of a cylinder. Yeah. So you can see here I have combined the helix and the cylinder on the same diagram, so you can see that it is spiraling here. You can also see this from inside, that there's a spiral, you know, around the cylinder. Okay, yeah. So yeah, this one is yesterday's example. Remember, xt equal to 3, yt equal to t, and zt is 2 minus t squared. This is yesterday's example here. So it is a parabola, right? It is a parabola on the plane x equal to 3, right? You can see here, it is this plane here. It lies exactly on the plane x equal to 3. Yeah. Let's sketch the one that we just discussed just now. Let's call this E3, E5. Let's call this GH. What is the one that we just discussed just now? The question, the final exam question. What is it?
1/4 cos t.
1/4 is 0.25 cosine t, right? Cosine t. What else?
Plus sinus t.
Sine t, right? Sine t. And then minus 4, right? Minus 4. Yeah, minus 4. And then t is from 0 up to 2 pi. That's why we have a complete ellipse, because t is from 0 up to 2 pi. Yeah. Okay. So with the arrow, it doesn't look. This is an ellipse, huh? But let me copy this one. Copy. Paste it here. What is it? Is it HT? Yeah, I call it HT. T from 0 up to 2 pi. Shift enter. There, you can see it is an ellipse there. And it is on the surface z equal to minus. Z equal to z on the surface, z equal to minus 4. Can also pull this to enlarge. Can also pull this sideways, to enlarge. Yeah. Okay, it is on the surface z equal to minus 4 there. Yeah, you can also rotate this. From above, it is looks like an ellipse from above. Yeah. Okay. All right. So enough on the vector curve sketching. So let's move on to this a new topic on derivatives. Yeah, derivatives of vector functions. Yeah. So later on we will see the integrals of vector functions. So suppose we have a vector function with components f1t, f2t, f3t. Then this is a function of t, right? And suppose f1, f2, f3 are differentiables. Then the vector function f, capital F, is also differentiable, and its derivative is equal to f1 prime ti plus f2 prime t vector j plus f3 prime vector tk. Okay, so we say that if the components are all differentiables, then the vector function is also said to be differentiables. Yeah. So but I think here we have derivative of dot product of two valued functions, and also we have derivative of cross product, okay, of two vector valued functions. So let me discuss these operations, right? These operations of vector valued functions. Before we discuss the derivative, let's first discuss these operations: addition, subtraction, multiplication, the dot product, and the cross product of vector valued functions. Yeah. So, for example, suppose we are given that ft, the vector function ft, is cosine ti plus sine tj plus k, and the vector function gt is equal to, say, minus sine ti plus cosine tj. I'm sorry, there's a t there, plus tk. Okay. Then what is the sum of this two vector valued function? What is the sum? Okay. What is the sum of these two valued functions? Sum, we add component wise. Okay, we add component wise. So therefore we have cosine t minus sine t I plus sine t plus cosine tj plus 2tk. Okay, that's how we add two vector functions. We add them component wise, component by components. Yeah. And suppose what is ft minus 2g of t equal to, what is ft minus 2g of t? We have cosine t plus 2, right? Plus 2 sine t for the component I. And what about the component j? We have sine t minus 2 cosine t, right here? Minus 2 cosine t. That's for component j. For component k, we have t minus 2t, which is minus tk. Yeah, minus tk. Yeah. Okay, these are some operations, addition and subtraction operations on two vector valued functions. Okay, next we want to find the dot product. What is the dot product of the vector functions f and g? So you need to recall how you find dot product of two vectors. Okay, this is given also in the book by Yusuf Yaqub in the appendix F. Okay, so if we have vectors A and B, And the dot product is A1 B1 plus A2 B2 plus A3 B3. So using the same idea, we have cosine t times minus sine t, right? The dot product. So we have minus cosine t sine t plus sine t cosine t plus t squared. Okay, so cosine t sine t, they cancel out, so it is equal to t squared. Okay, so this is a dot product here. This is a dot product, and dot product is always a scalar. Always give us a scalar function. Okay, the result is always a scalar. I mean no vectors. The result is not a vector, but it is a scalar. Okay, next we have the cross product. How to determine the cross product of two vector functions. So recall the cross product of two vectors. Okay, if A and B there's two vectors with the components respective components here, then the dot product, the cross product is equal to the determinant. Okay, is equal to the determinant, the first row of a matrix. The first row of the matrix is the unit vectors I, j, k. The second row are the components of vector A, and the third row is what? The third row are the components of vector B. So using this definition, so we calculate the first row consists of the unit vectors I, j, k. The second row are the components of vector F, cosine t, sine t, and here t. And the third row are the components of vector G, minus sine t, cosine t, t. Okay, so what is and the result is a vector. Okay, the cross product of two vectors is also a vector. All right, do you still remember how to find the determinant of a 3 by 3 matrix? What is one technique? One technique is to what? Is to write down the first two columns, right? Beside the determinant. And then we multiply, okay, in this direction. We do one multiplication in this direction to get what? T sine ti, and then we multiply this direction, plus, we use plus sign. What is that? Plus, here we have minus t sine tj, yeah. Here we get minus t sine tj, and then we multiply these three elements to get cosine squared tk plus cosine squared tk. Okay, all this in the using plus sign. Next, we multiply in the upward direction, and then using with coefficient minus 1. So what do we get? We have minus sine squared tk, right? Minus sine squared tk. And then we multiply these three elements also to put a minus sign. What is the product equal to? T cosine Ti. Finally, the product of these three elements. And then what is the product? T cosine Tj. T cosine T j. And now we combine all the like elements. We have two terms containing I. So the sum is what? T sine T minus is equal to T sine T minus cosine Ti. Okay. And what about the component J? We also have two components J, minus T sine T minus T cosine T. So we can factor out minus T sine T plus cosine Tj. And then finally the remaining components are with K. We have cosine squared T plus sine squared T there, right? Which is 1, isn't it? Cosine squared T plus sine squared T is equal to 1. So that means plus K. So that's the result. Any question? And suppose there is also another function, a scalar function, a real value function, ht equal to square root t. So we can also form a composite function. For example, f h of t, okay, where ht is square root t. So in the function f of t, vector function f of t, we replace t by cosine by square root t. Yeah. What else? We have sine square root t j, and then plus square root t k. Okay. Yeah. So in the vector function ft, we replace each t by square root t. So that is the result here. So these are some basic operations on vector valued functions. Yeah. Any question?
So far, so good, Doctor.
So far no. Clear tak?
Okay. All right. Okay. Okay, we have this. Now we look at derivatives of vector functions. Okay, so I've already explained to you, given a vector function f, its derivative, to find its derivative, we differentiate the components, okay, of the vector functions. Yeah. So, for example, so suppose we are given a vector valued function g of t equal to ti plus t sine tj plus e to the minus 2t k. Okay, So what is the derivative of the vector valued function g? So we differentiate component by component. Okay, we differentiate t, and we also differentiate t sine t, and also we differentiate e to the minus 2t, right? So we differentiate component by component. The derivative of t is 1. What about the derivative of t sine t? We use the product rule there. Okay, use the product rule. I hear some noise in the background by Muaz. Muaz, are you saying something?
Sorry Doktor,
Ada nak tanya apa-apa ke?
saya lupa off mic tadi.
Oh, okay. Okay, what is the derivative of t sine t? We use the product rule. Remember the product rule for derivative? It is here we have u prime v plus uv prime. So that gives sine t plus t cosine t. What is the derivative of e to the minus 2t? Which is the chain rule? The derivative of the exponential, the outer function is the exponential function, the inner function is minus 2t. So it is minus 2 e to the minus 2tk, right? Yeah. And we can also differentiate this again. A g prime t here is again a vector valued function. Of course, we can differentiate this again, right? Yeah, to get g double prime t. And suppose it is required to determine g prime pi. What is the value of g prime pi at t equal to pi? So we substitute t equal to pi. And simplify. Sine pi is 0. Cosine pi is minus 1. So we have I minus pi j minus e to the minus 2 pi k. Okay? Yeah. All right, suppose we want to find the second derivative. Then we differentiate g prime. Okay, we differentiate g prime t. The component function for the vector I is a constant, right? It's constant, so it's 0. It's 0. So 0. Can write this as 0i. Later we can drop the I symbol there. Then we want to differentiate sine t plus t cosine t. Differentiate sine t, we get cosine t. To differentiate t cosine t, we use the product rule again. So we get cosine t minus t sine t. And then differentiate the component of k, we get what? Plus 4, right? This time we get plus 4 e to the minus 2t. Okay, so this is equal to 2 cosine t minus t sine t j plus 4 e to the minus 2tk. Okay, so there is no vector I there. That means the coefficient of vector I is equal to 0. Right? And of course, you can differentiate this again to get third derivatives and so on. Right? Yeah. So that's how we differentiate a vector function. We differentiate component by component. Right? So we have what's shown here, listed here, are some product rule or some rules of derivatives involving vector valued functions. Yeah. So this A here, this part A here shows that the derivative of a sum is a sum of derivatives of vector valued functions. Yeah? And if we want to find the derivative of a scalar function h, okay, h here is a scalar function. Assume okay, this we must make this assumption in the beginning. Assume that the vector valued functions capital F and capital G are differentiables, and assume ht and ut are scalar functions. These are real valued functions, and assume that also differentiable. That means their derivative exists. Yeah. So for part B, if we have a scalar function h times the vector valued function f, then the derivative of this product follows the same product rule that you have seen in for functions of single variables. Yeah, they obey the same law here. And what's shown next is the derivative of a dot product. Okay, the derivative of a dot product vector function f with vector function g also follows the same product rule. Same product rule as for function of single variable. And in part D, we have a derivative of a cross product of a vector functions f with a vector function g. And again, it follows the same product rule, right, for functions of single variable here. And the last part E is a chain rule. We have a vector function f of a scalar function u. So its derivative is according to the chain rule. Okay, obeys the same chain rule that you have seen in for function of single variable there. Okay, so let's see some examples of derivatives of vector valued functions.
Doktor,
Yes.
kalau cross product tu dia punya produk tu kita kena guna determinant tu maksudnya.
Yeah, betul. Okay. That means you have to use the determinant, right? In order to evaluate this cross product here.
Okay.
Yeah. Just now I showed you one example, right? Of a cross product of two vector functions. We use determinant, isn't it? Yeah. So the same thing here. Okay. You need to use the to evaluate these two cross products using determinant. Yeah. Any more questions? All right. Thank you for asking. Let's see an example. Okay. Give us let ft be a vector function equal to the inverse tangent of t times a vector I plus 5k. So there is no vector j here, right? So that means the coefficient of vector j is 0. And let the vector function g equal to I plus ln t j minus 2tk. Yeah. So we want to determine f dot g prime of t and f cross G prime of T. Yeah, we want to determine the derivative of the dot product of F with G and the derivative of the cross product of F with G. Yeah. We have two methods, right? We have two methods of calculating the derivative of F dot G. One way is to calculate F dot G first and then take its derivative. Okay, one way is to calculate the dot product of F with G first and then differentiate the result with respect to T. So what is the dot product of F dot with G? Is tangent. Remember the dot product? Tangent is a scalar, right? It is a scalar. There's no vector J, so it's 0. Minus 10t, isn't it? Minus 10t. This is a scalar, right? Yeah, scalar. Can you see that?
Yes. Yes.
Okay, now we take the derivative. We differentiate this. The derivative of tangent t is the inverse tangent t is 1 over 1 plus t squared minus 10. Okay, that is the result. Another way is to use that product rule. Yeah. Alternatively, we can also use the product rule or the dot product of two functions. It is equal to f prime t times a dot product with g of t plus f t dot product with g prime of t. Okay, let's use this approach to verify the previous result. So what is f prime t? F prime t, you differentiate component by component. 1 over 1 plus t squared, right? I. That's all, right? That's all. Because 5 is a constant, if you differentiate 5, you get 0. What is g? G is given as I plus ln t j minus 2tk. Okay, this is a dot product. And then plus f of ft dot g prime t. Now, ft is the inverse tangent t, I plus 5k dot product with g prime. What is g prime? G prime is okay, let me write it down here. This means what? F prime t is 1 over 1 plus t squared I only, right? For g prime t, it is equal to 1 over t, differentiate component by component. So this is, that is g prime t. Yeah. So here I need to write down 1 over tj minus 2k. Okay, so next we determine these two dot products. The first dot product is 1 plus 1 over t squared, isn't it? And the second dot product is minus 10, right? Minus 10, yeah. So we have the same result. Using the first method, okay, we have the same result here. Any question?
No, Doctor.
No. Okay, what about the derivative of the cross product here? Okay. Next, we want to find the derivative of the cross product. So one way is to find the cross product first and then differentiate. Okay. One way is to find the cross product first and then we differentiate. And the second method is to use the what? The product rule. Yeah. Yeah, the product rule for derivative of f cross g. Okay. So what is f cross g? You want to use the first method, we find f cross g first. What is f cross g? The top row is the unit vectors I, j, k. Okay. The second row is the components of vector f. The components of vector f. Inverse tangent. And the inverse tangent. What else? We have 0, 5 there, right? And for the third row is the component of vector g, which is 1 here, ln t, and then minus 2t there, right? Minus 2t there, yeah. So let's use the same technique we have used previously. We write down the first two columns on the right hand side of this determinant. And then we form the product of three elements. Okay. So what is that product? 0, right? 0i. Next, this product here is 5j. Next is the product of these three elements here, which is ln t. The inverse tangent of t times vector k. Next, we determine this product in the upward direction is minus 0k. Is minus 0k. And then we the product of the next three element, minus 5 ln ti, right? Minus 5 ln ti. And lastly, this product here, which is what? Minus 2 t, the inverse tangent of t times j. Now, And then we combine all the like elements.
Doctor, there is plus, right?
Yeah. Apa dia?
Plus 2t.
Minus, oh yeah, because upward here is we use minus sign, right? Yeah, you're right. This should be plus. Thank you. Thank you. Should be plus, yeah. Okay, now we combine all the like terms. We have minus 5 ln ti. What about j? We have 5 plus 2t inverse tangent of t j. As for k, we have ln t tangent inverse t for k. That's all, right? That's all. And then to find the derivative of f cross g, we differentiate term by term. So we differentiate term by term. So the first term is minus 5 over ti. The next term is, let me just show you what the result is. It is equal to, we have 2t over 1 plus t squared plus 2, yeah, plus 2, the inverse tangent of tj. Next we have 1 over t, apply the product rule again, plus ln t over 1 plus t squared. Okay. Okay, so that is the derivative of f cross g. Alternatively is to use the product rule for f cross g. It is f prime t cross g plus ft cross g prime. Of course, this involves evaluation of two determinants, yeah? So I leave it to you to try this out and show that it leads to the same result as in the first approach there. Okay, let's do one example related to the chain rule. Yeah. Given f, the vector function ft equal to ln ti minus 4e to the power of 2tj plus t minus 1 over tk and g of t equal to square root of t. Okay, we want to determine f, the derivative of f of g of t. Okay, yeah, you have a composite function here now. It's a composite function. Well, one way is to first determine FGT and then differentiate. Okay. So one method is to first evaluate g of t, where g of t is square root t. Okay. So in the function ft, we replace t by square root t to get e to the power of 2 square root t plus square root t minus 1 over square root tk. It's a j here. And then differentiate, right? And then differentiate. Differentiate component by component. Another more efficient method is using the chain rule. Using the chain rule. What is it? Can g of t is equal to d du f of u, fu, right? Fu, and then times du dt, where u is equal to g of t. Yeah, we let u equal to g of t and then differentiate u with respect to t. Okay. Yeah. And what is fu? Fu is what is fu? Just replace t by u. In the definition of ft, we replace t by u, so we get ln u I minus 4e 2u j plus u minus 1 over u k times du dt. Yeah, u is g of t. So to find du, we differentiate component by component. So we get 1 over ui minus 8e 2uj. This is the same as 1 minus 1 over u, right? U minus 1 over u. So the derivative is equal to what? U plus 1 over u squared k. And what is du dt? U is g of t, which is square root t. So we want to differentiate square root t. Okay. So this is what? This is the same as 1/2 t to the minus of a half, which is 1 over 2 square root t. Next, we replace u by square root t. So we get 1 over square root t I minus 8e 2 square root t. U squared is equal to t. And multiply this with 1 over 2 square root t. So that's the result. Okay, this is the result. Oh, I'm sorry, there's a j here. There's a j here. So this is an example of a chain rule, or application of chain rule for the vector function. Yeah, vector function. Any question? Okay, one application of derivatives is this is the velocity given a function r, which represents the position vector. Remember yesterday I said that the vector valued function can be viewed as a position vector, yeah, to describe a curve, the motion of a point in space, yeah. Given a vector valued function r, so as t varies, the tip of the vector also varies from time to time. So the tip of the vector traces a curve in space, okay? That's something as shown here. So if r represents a velocity, represents a position vector, then the velocity vector is r prime t. Okay, it's the derivative of the position vector r. So it is equal to x prime t plus y prime t plus z prime t. And the speed is equal to the modulus of the vector v. Okay, so the modulus of a vector is the square root of the sum of the squares, yeah, of the components, yeah. And from the velocity vector, we can differentiate the velocity vector to get the acceleration vector here, at. Yeah. So at is v prime t, or also equal to r double prime t. Yeah. So it is equal to the result is as shown here. So let me do an example. After that, we stop. Given the position vector, was also sometimes called a position function vector, or sometimes also called the position function of an object by, say, rt equal to cosh of t. Okay, this is a hyperbolic function, plus shin of t, also a hyperbolic function, plus tk. Okay. So what is the vector, the velocity vector v? Is equal to r prime t, which is equal to, what is the derivative of cosh? You still remember? What is the derivative of cosh?
Sine.
Shin,
Sine.
shin.
Sine hyperbolic.
Some students call it shine. I call it shin. Yeah, shin.
Shin. Okay.
What about what's the derivative of shin?
Push.
Cosh. Yeah. Oh, sorry. It should be shin t times j. Okay, and then plus k, isn't it? Okay, what about the speed? The speed is equal to the modulus of the velocity vector v. So it is a scalar, the square root of shin squared t plus cosh squared t plus 1, isn't it? Can we simplify that? We have an identity. Remember one identity that says that cosh squared minus shin squared t equal to 1, isn't it? So 1 plus shin squared t is equal to 2 cosh t. Yeah. So using that identity, this becomes 2 cosh squared t, which is equal to square root 2 cosh of t. Okay, cosh of t, because cosh t is always positive. And then finally, what is the acceleration vector? is equal to the derivative of the velocity vector. So differentiate the velocity vector, we get cosh t I plus shin t j. Okay, that's all. There's no vector k here. All right, so these are just some simple applications of derivatives. So if you look back at our lecture plan, I'm not able to cover everything here. We have already discussed a graph of vector function, differentiation, velocity, acceleration. I'll discuss the others next week. Integration of vectors, vector tangent, and vector normal. There's not enough time this week, so I will discuss them next week, inshallah. All right, so do you have any question before we stop?
No, Doctor.
For me,
I've given okay. I've given you a third assignment. Yeah, I haven't marked them because yeah, I need to give the fourth assignment soon. Yeah. I mean, don't wait for the assignment that I give you in order for you to practice. You can try the sample test, sample final exam, or the questions in Dr. Yusuf book. You know, you can also try them out. And you have question, we can discuss. We can discuss. You know, you can ask me through WhatsApp, and then I try to answer them. Also, try in the WhatsApp. Okay.
Okay, Doctor.
Okay. So,
InsyaAllah.
inshallah. All right. So now let me show you your attendance. There you are. Okay. Please scan your QR code for the attendance. And you may leave this online class after you have finished scanning.